So the last few sections of this chapter deal with oscillations and waves. Chapter 15 is called a simple harmonic motion, and we'll talk specifically about what that means as we go. But we start out by just talking about periodic motion. Periodic motion is motion that repeats itself on regular time intervals. So, like a pendulum, right? A pendulum swings across, it comes to a stop over here, and then it swings back, right? And so the time for one complete oscillation, in this case over and back, is called a period. And so it's the time for one complete oscillation. The frequency is 1 over the period, or the number of oscillations per time. So the units for period is just seconds. The SI unit, any time interval of course is fine, any time unit. The unit for hertz, the SI unit is 1 over second, the unit for frequency is 1 over seconds or hertz. A hertz is just an inverse second. And so, you could say, well, if the period is 2 seconds, then that means the frequency is 1 over the period, which is 1 over 2 seconds, which is 0.5 hertz. Right? And so this is saying the period is 2 seconds, and this is saying there's half an oscillation per second. Right? So you can do an example where let's say the period is for some ultrasound wave is 0.4 microseconds, right? Which is 4 times 10 to the minus 7 seconds. Right? Well, then the frequency is 1 over 4 times 10 to the minus 7 seconds, or is equal to 0.25 times 10 to the 7th hertz, because a 1 over a second is a hertz, which is 2.5 times 10 to the 6th hertz, or 2.5 megahertz. This is saying that there's an oscillation every 0.4 microseconds, or 4 times 10 to the minus 7 seconds. This is saying because of that, there are 2.5 million oscillations per second. So let's start talking about simple harmonic motion. Harmonic motion is just oscillatory motion, basically. Simple harmonic motion sort of specifically means the acceleration of the system is proportional to the displacement from equilibrium. That is to say, for example, if you have a spring and it's in its equilibrium position, then the force either pushing this way if you squish it or pushing this way if you stretch it is proportional to how far it's stretched or squished. This is Hooke's law, right? The force, the acceleration, which is the net force is proportional to the displacement. And so that's what we call simple harmonic motion. And springs are a good example of that. It turns out a pendulum is also a pretty good approximation to that type of motion. And so what happens is I release the mass, and because I've stretched it, it's getting accelerated in this direction. The net force, at least in the horizontal direction, is to the left, right? It's back at equilibrium here, but it's moving in this direction. Even though the net force on it is 0 in the horizontal direction because it's at equilibrium, it's zipping along this way, and so its momentum carries it forward until the spring, when it gets past equilibrium, pushing this way, causes it to stop and start accelerating in the other direction, so it oscillates back and forth. It turns out that the motion of an object that does that is given by it's given by the equation a cosine of omega t plus phi. Omega is just 2 pi over the period, and it's called, or it's 2 pi times the frequency. So again, if x is the position of this thing, then it oscillates back and forth like a cosine. A is the amplitude, and so A is sort of the maximum distance it can go. And so, you know, it might be at A here, and here it might be at minus A, for example. If those are the extremes, right? It oscillates back and forth between those positions. And so cosine goes between -1 and 1, and so its maximum value is A, its minimum value is minus A. And it oscillates back and forth between those, just like this function does. And you can see that with this definition, that is to say, let's drop this term for a second. Let's leave that out. This is called the phase, and I'll talk about that in a second. But if I just write that x of t is equal to a cosine of 2 pi divided by the period times t, we could easily see that, look, every time t increases by 1 period, like if the time, this represents time, right, and this is just the period of oscillation, like 2 seconds or 3 seconds or whatever it is, however long it takes to do one complete cycle, then you can see that every time t increases by a multiple of the period, every time the time increases by the multiple of the period, the oscillator will have gone through one more full oscillation. So t is 0, its position is A. If t is if the time is big T, those two cancel, it's 2 pi. I'm back to A again. Similarly, if this is twice the period, if I wait for 2 periods, this is just another multiple of 2 pi, which gets me back to A, and so on. And so anytime this is a multiple of this, I get back to my original position, right? And of course, if it's anything in between there, it goes it's somewhere in between. When this is half a period, when t is big T over t, sorry, when time is capital T over 2, so I can say, look, at t equals the period over 2. Let me write that a little better. Then if I just wait for half a period, or any, n plus a half, where n is an integer, any n plus a half of the period, my x of t is going to be at minus a. In other words, it's going to be at the other end. If I'm at the left side, where I'm at minus a, and then any integer number of periods above that, like a half period or 1.5 periods or 2.5 periods or 3.5 periods and so on, I'll be back at minus a. And so you can see that this function puts the spring like a cosine oscillating between these two positions. So let's dig into the math a little bit and look at the period and frequency of a mass on a spring. And we're gonna start by looking at some differential equations here first. And so let's just talk about this for a second. First of all, we're gonna set aside the forces in the y direction, which is the normal force and the force of gravity, and we're gonna just look at the horizontal direction force, which is F equals minus Ka, as Hooke's law. And so we can write the sum of the forces in the x direction, which is just the one force. It's just minus kx. And so I can come down here and say minus kx is equal to ma sub x. Well, the acceleration in the x direction, if we take a calculus approach now, right, rather than delta v over delta t, we can say, look, the velocity is dx dt. The acceleration is dv dt, which is the second derivative with respect to x. And so it's this is m times d squared x over dt squared. And so what we get, if I take the two endpoints here, is m times the second derivative of x with respect to time equals minus kx. Right? And this is called a differential equation. And you've already done differential equations, because a differential equation is really any equation that has a derivative in it. And so there's nothing super fancy about it, but there it is. And so we can put both terms on one side, and we can say, well, m times d squared x over dt squared plus kx is equal to 0. And we can divide through by m just to simplify it a little bit, and we can say d squared x over dt squared plus k over m times x is equal to 0. And now we're asking the question, well, is there a function x that depends on time, right? X is the position, and we know the position of this oscillating object is time dependent. And so is there anything that, is there any function whose second derivative added to a constant times the function itself gives you 0? And I'll just give you one. First of all, I'm going to pick, I'll tell you why in a second, but I'm going to pick omega as a square root of k over m. So this gives me d squared x over dt squared, plus omega squared x is equal to 0. And I'm going to say, functions. You already are aware of functions whose second derivative is, when added to the function itself times a constant, gives you 0. And that's, hopefully you've seen these. Oops. A and phi naught are constants. We sometimes call them integration constants, but they're constants that are to be determined by our problem. And so just to be clear on this, we're going to go back and we're going to write. We're going to take the derivative of this, and so the derivative of this is a constant times sine. So the derivative of sine is cosine, and so this is going to be a cosine of omega t plus phi naught, right, times the derivative of what's inside, which is omega. And so it's omega a cosine of omega t plus phi naught. That's the first derivative. And then the second derivative, you can leave the parentheses, t parentheses, or leave it off or leave it in. So to take the second derivative of this function, derivative of cosine is negative the sine. I'm going to get another omega for the term inside, and it's going to be minus omega squared a sine of omega t plus phi naught. That's what the second derivative is. That's equal to minus omega squared x, because x is a sine of omega t. And so this means that d squared x dt squared plus omega squared x is equal to minus omega squared x plus omega squared x, which is 0, which verifies that this function solves this equation. By the way, you can check for yourself. We could have just as easily picked a cosine in here. You can vary between a cosine and a sine just by changing this phase number. If you make it a pi over 2, that makes it a cosine, or vice versa. I can't remember. So this gives you the freedom to pick either sine or cosine there, and the phase shift will become a little different. I'll give you some examples of that. And so that means that physical systems that obey this physics, this picture where the sum of the forces is minus kx, and that's equal to ma, have these solutions. It turns out there are many, many systems almost all vibrational motion in buildings or anything has this sort of behavior. Lots of oscillatory systems of all different types have this physics, and so understanding this problem is important in a lot of areas of physics and chemistry. Vibration in molecules and things like that are all fairly close to sine functions. So this is a display of the solution to the simple harmonic oscillator function. If you look down here at the bottom of the page, it's x of t, that's x, the position of the oscillator. So this is a mass vibrating on a spring, say, oscillating back and forth, the position back and forth. The position as a function of time is given by the function a sine of omega t plus phi, or phi, where a is the a and phi are coefficients, and omega is, as written up above the curve here, is 2 pi over the period. Again, the period is the time it takes for one complete oscillation. So, you know, if you stretch the spring out and release it, it's the time it takes to go all the way in and be compressed and come all the way back out again and be back to its stretched form. This is a graph of the vertical axis is the position, the horizontal axis is time, and you can see as time goes by, the oscillator will oscillate between the minimum and the maximum. Let me pick a few reasonable values for this. We'll set our amplitude to say 2, right? I'm going to move the phase over here to 0. We'll talk about that in a second, right? And we'll pick some value for omega that's a little more stretchy than that, like this. And so when you look at this, you can see that, okay, the amplitude here is 2. It's just 2 times the sine of omega t plus phi. Again, the sine function just varies between -1 and 1, and so the amplitude just tells how far it's going to go between equilibrium and its maximum or minimum value. And so I can adjust a to say 3, and you'll see that now the thing oscillates between -3 and 3, and so on. I can pick any value for that, right? Maybe I'll pick 2.5 or something like that. And so that's what the a does in the solution. Now let's look at omega. Omega is 2 pi over the period, and we talked about that in the notes a little bit. So if I make omega smaller, that means the period's getting larger, and so as I slide this slider to the left, you will see the wavelengths get longer, because that's the time between the time between peaks is the time it takes the mass to go under one full oscillation. In fact, that's also the time between troughs, or the time between halfway up the slope to halfway up the slope, and so on. As you can see, this starts at 0, and so one full oscillation is a little more than 5 seconds, the way I have it set up now. And so you can see this looks like a sine function. If you notice over here on the right, this variable phi is set to 0, and so the graph is just a sine of omega t, where omega and a are given and t is just allowed to vary. And so I get a sine function. And so that brings us to phi, or phi. Right now at 0, watch what happens as I move it. I'll increase it, and you'll see the curve moving to the right. Now if I set it to 1.7, which is pi over 2, you'll see that now this graph looks like a cosine. At 0, it's at its maximum, like a cosine is. Cosine of 0 is 1. And then it goes to its minimum and maximum, and so on. Similarly, I could slide it to the left and go to negative pi over 2, and now it would be at its negative maximum extent, 2.5, at t equals 0. And so these three parameters, a, the amplitude, omega, the angular frequency, and phi, give me full freedom on this function to solve any harmonic oscillator problem. I can have any amplitude, any frequency, and I can have it at 0, its position at 0 for any value. So this is what we have here now is a spring that's been compressed, right, into a squished position as being released. At t equals 0, it's at its minimum position, it's released, and it oscillates back and forth. When I went to t equals 1.57 up here, t equals pi over 2, right? Now it's being stretched to its maximum and released, and so it falls back in past its equilibrium position and goes to a squished position, and then it races back past its equilibrium to a stretched position, and so on. Right? When it's at zero, it's back to looking like a sine wave. And what this is saying is that at t equals 0, the mass is at position 0, but it's got a velocity. This is a position versus time graph, and so the slope here is the velocity, and so this might be like you hit it with a hammer or something at t equals 0, or it was just set up oscillating at some negative time, and so at t equals 0 it's moving past its equilibrium position, and so on. We'll talk in a little bit that since this is a position versus time graph, the slope of this graph is the velocity of the mass, and so we could take a derivative of this function and get the slope. Furthermore, and get the velocity. Furthermore, we can take a second derivative of this function with respect to time and get the acceleration.